Hello, my name is Wieslaw. In this video you're gonna learn Number 1. How to easily visualize a linear form in algebra. Number 2. How to graphically determine the value of one form on a vector. Number 3. What does the concept of linearity of form mean? You should watch this video because we'll use simple drawings and animations to make abstract linear forms easier to understand. So you will be able to grasp the concepts of the line and surface integrals more easily later. So at the beginning, before we give any definitions, let's see how to imagine the simplest such forms. We will start with an ordinary two-dimensional affine plane called R2. At each point there is a vector understood as an arrow pointing in some direction. Then we can imagine linear form as a set of certain lines that are parallel to each other and equally spaced. We can also say that a certain positive direction is given for this family of lines. Of course, it is a matter of definition in which direction we will take this positive direction. We can take this line as the zero line. There will be a first, second and third line. Of course, they could be created in this way to infinity. You could also create lines with negative numbers here. For now, we are not interested in exact definitions because people often use very complicated formulas and don't understand that the idea behind them is very simple. So we have a certain positive direction in this family of lines as numbers increase. Let's write negative numbering, -1 here, -2 here, and see how will this one form act. When we take any vector in this plane, let's say that this vector starts on this line, number 0, and somewhere here it reaches the line number 3. In linear algebra, it is said that the one form is a linear function on vectors. You can think of it as a linear machine that takes in a vector and puts out a number. Now I'm gonna show you graphically how to produce that number. It simply will be the number of straight lines that V is crossing. However, if the vector starts on some straight line, we can start counting from the next straight line, so we look at how many red lines this blue vector is crossing. We don't take the zero line into account, so we have here 1, 2, 3. We can denote the form here as phi, and we can write that the value of this abstract form phi, which is a family of lines on the vector v, this value is equal to 3. You can see that the form will be an algebraic object, which of the vectors will give us numbers. And this is the most important information which you need to remember here. Well, to make it easier for you to understand, let's take another vector directed somewhere else. Let's start it here and finish here, halfway between the straights. Even though we firstly imagine the form as a certain family of lines numbered in this way, we will ultimately imagine it as a family of continuous lines in the sense that between the line number 0 and line number -1, there is of course a line number -1/2. So we don't have discrete but continuous numbering for the lines. If we want to find the value of the form on some vector, which we will denote here W, these vectors we understand as vectors attached to a given point. If a given vector is directed opposite to the direction in which the numbering increases, then the values must be taken negative. So we count that here the vector once intersected the line, but in the negative direction. So we have -1. The second time it intersected the form line, so we have -2 and half times. So in total we have -2.5. And we can then loftily say that the value of the same form, but on a vector w, is equal to -2.5. And of course we could also do this for any other vectors. In general, the value of the form for a linear combination of vectors is to be a linear combination of form values on each vector separately. In practice, it means first, in the drawing, that if we move this vector w to the end of the vector v, so as to create their sum, and the sum is gonna start here and have the tip here. If done precisely, it would turn out that this arrow ends halfway between these two lines. So, if we calculate the value of this form on this green vector, because this green arrow is directed according to the direction of the one form, the value of this form on the green vector is equal to +1/2, and this value is of course consistent with the sum of the values of one form on these two vectors separately. We can write it down that phi of v plus phi of w is equal to 3 minus 2.5 equals 0.5. And this is equal to phi on this green sum vector. It was created as v plus w. It was the vector that we can mark in green, for example as u. We just see what the linearity of forms is all about. These lines are not some kind of bent curves, but are straight lines. This guarantees us that such operation will be linear, of course, but this is only one of the possible interpretations of forms. Sometimes, if vector spaces are more abstract, then we cannot imagine it in such a naive way. Nevertheless, in most applications of such classical physics, in electrodynamics, or even in the theory of relativity, such an interpretation is completely sufficient. Here we have it in 2 dimensions, but of course it can now be generalized to any number of dimensions. Let's draw a 3-dimensional coordinate system. And of course, in 3 dimensions, we can also create a function which turns the vectors into numbers, and here in such a way that we will count this time how many times the vectors intersect certain planes. So we can represent a linear form in 3 dimensions as a set of parallel planes. I symbolically draw it here. Of course, we mean a continuous family of planes, but we can only mark planes labeled by integer numbers. And of course enter some numbering here. Let's say 0 this plane here. The next one it will be 1. Then it will be 2 and so on. Then there are also planes with negative numbers. So this form can be considered as a map with some direction. And for each of these planes, there is a certain positive side and negative side. And again, when we take any vector which, let's say it would start on this plane and end with the last one I drew, then we will say that the value of the form phi on this vector, which we will denote by v here, this value would be equal to 3. Later in further recordings, I will show you some examples of such forms in electrodynamics, so that you can also see that these forms are indeed sometimes real physical fields. But these forms are also useful in mathematics when calculating line integrals or surface integrals. It's a very useful concept, and thanks to this concept we can easily introduce orientation when integrating. Then it's a natural thing. So this is a graphical interpretation, of course. It could then be extended to a larger number of dimensions. I won't do that now so as not to bore you. Traditionally, well, this is really talked about at any lectures, but at a standard linear algebra lecture, it is usually said that if a vector space V is given, we create a so-called dual space for it, that is a space with an asterisk as the space of all linear maps from this vector space V to real numbers. Of course, it is true what is written here, but nevertheless, it was worth starting with some pictorial interpretations and not immediately writing the most abstract definition. Then this definition is also needed to summarize this knowledge and in order to be able to operate with it in a strict way. So the forms are to be linear mappings, in other words, linear functions whose argument is what we insert into the form will be vectors, and what we get as a result of the form's operations are to be numbers. And the fact that these are linear mappings means that for any form phi belonging to this pompously named dual space, the space in which these forms live, we call the space of all possible arrangements of these families of lines for all possible directions here on the plane, the space dual to the space R2. For each such form phi, the value of this form phi on a linear combination of vectors, meaning if we take two vectors and multiply them by a number, some number a times v plus b times w, is equal to a linear combination of values of phi on each vector separately. It will be a times phi of v plus b times phi of w. However, of course, this condition can be broken down into the condition that the value of the form on the sum of vectors is to be the sum of values of phi on each vector separately. And the value of the one form on the a times v, it should be a times phi of v. And it is a very simple matter, because multiplying the vector v, let's say by a positive number, this is creating a vector in the same direction, piercing a times more form surfaces. But if a is negative, then of course the vector av will then be directed in the opposite side, and then the positive value of one form on the v vector multiplied by a negative number will then give a negative value. So much for the introduction. In the next video I'll show you an interesting pictorial method on how to add one forms and how to multiply them by numbers. If you have any questions, feel free to comment below. Thanks for watching. Don't forget to like and subscribe.